In this unit, we're going to continue our look at optimization problems as we just started in the last unit. And in particular, we're going to focus on the algebraic side of things with a bit of visualization thrown in for good measure. What we're going to do is try to generalize what we saw in the fall term or first term, the idea of critical points and the idea of classifying critical points with derivative tests, and then applying those techniques and ideas to a variety of word problems as we go through the unit. So one of the things we have to do first, if we're trying to find a maximum or minimum of a function, is find out where the critical points are. And we noticed in the last unit that if we had a minimum, say we had contours that were going down, a minimum at the center here would have a gradient equal to the 0 vector, or the 0, 0 vector if we're talking about a function with two inputs. And those are the equivalent of the setting f prime of x equal to 0 in single variable or one variable functions. And in those scenarios, we would take the derivative, set it equal to 0. Now what we have in the gradient, of course, is two derivatives. We have the x derivative and the y derivative. And we're going to set both of those equal to 0. That's going to be our condition for the gradient equaling 0. Let's start this off with an example to make it concrete. We've got a function that's got a combination of various x powers and y powers and x and y products, and we're simply going to identify the critical points. And what that means is setting grad of f, setting grad of f equal to 0, 0, or, if you like, setting, in this case here, they are x and y, the explicit variables, setting fx equal to 0 and the y partial derivative equal to 0 as well. Okay, so that's our goal if we're going to identify critical points, which are potential mins and maxes, and we just go ahead and do that. From our function, the x derivative is 4x cubed minus 4y. The y derivative is 4y cubed minus 4x. And then remember, this is an action that we're doing. These derivatives are a simple property of the function. If I give you the function, these are the derivatives. What we're doing next, something that we're choosing to search for, is by setting these values equal to 0, we want to say, we would like to look for critical points. So we set these values equal to 0. So looking for critical points. So we set fx, fy equal to 0 and try to solve for the points for x and y. All right, so let's do that here. Set those equal to 0, and if those are equal to 0, then what can we conclude? Well, here we conclude that 4x cubed is equal to 4y. We can cancel the 4s, so x cubed must equal y at the critical point. And likewise, for the other expression, I can bring this 4x over, and this would tell us that y cubed must equal x. We must satisfy both of these equations. And if that's the case, we can number them and try to sub one into the other and see where that gets us. Let's take 1 and put it into 2 here. Y is equal to x cubed. So what we have here is x cubed, all cubed, must equal x. So this y cubed here, we replace it with each y with an x cubed, and then we cube it. So we have x to the 9 equals x, or a few different ways to look at this. Some people might just observe the solution. Certainly 0 is a solution here. I think I'd like to put it in factored form because that makes it more explicit what's going on. Let's set this equal to 0. Then we have x minus x to the 9. And if that's the case, then we can say 0 is equal to x, 1 minus x to the 8. Once it's in factored form, we can identify the solutions, either x equals 0 or 1 minus x to the 8 equals 0. The only solutions for this are x equals 1 or minus 1. They're the only values that when I put them to the 8th power are going to cancel with a 1. So those are our three x values. And let's actually do this on another page just to be certain that we've got all this. Sorry, there we go. So for the x equals 0 condition and x equals 1 and x equals -1, those are the three possibilities that we found would satisfy both equations. We would have to have a matching or corresponding y value, and we said earlier that the y value would equal x cubed. That was our one equation. We're going to get into some, I don't know about complicated logic, but certainly some intricate logic with some of these problems where sometimes we pick one condition, sometimes we pick another. It's always worth trying to be, well, it's always worth being careful in math, but in particular, I would warn you to be careful about the solving of these kinds of equations. It's something that a lot of you have done before, but maybe not had a lot of practice on, especially with nonlinear equations, like we're going to see in this section of the course. So I'll talk about it more in a second, but just be careful as you solve these equations that you're including all the solutions you're supposed to and none of the ones you aren't. All right, x equals 0, and we got this value by relying on y equals x cubed. So the y value that would match that would be 0 cubed or 0. If x was 1, then y would be x cubed, which is 1. And last but not least, if x is -1, then our y value would also be -1. So the points 0, 0, 1, 1, and -1, -1 are all critical points. Now here's where I would say check it before you go further on a problem. You're going to do a lot of work based on these, so make sure you have the right critical points before you go too far. And how can we check that? Well, fx, the x derivative, was 4x cubed minus 4xy. And the y derivative, y partial derivative, sorry, it was times 4y. And the fy derivative was 4y cubed minus 4x. And if we just check the 0, 0 point, the 1, 1, and the -1, -1, 4 times 0 minus 0, yep. 4 times 0 minus 0, yep. 1, 1. We want these to be equal to 0 to be critical points. 4 minus 4, yep. 4 minus, and we see the same pattern again. Even the cubed keeps the sign the same, so this would be -4 minus -4. Things cancel. So checked. So these 3 points are in fact critical points. When I use them in our derivatives, we get the x derivative and the y derivative simultaneously equaling 0. Okay, so that's how we can find critical points, by finding the derivatives, all the partial derivatives, setting them equal to 0, and trying to solve for the points. Here's a picture, contour diagram, of the surface for this function. If you take a look at it, well, we don't have the axes on here, but we know where the critical points are. We said the critical points were at 0, 0, 1, 1, and -1, -1. Simply by looking at the shapes of the contours, it's clear that there's a critical point somewhere in the center of this blob here. There will be another critical point in the center of this blob here. And the only thing that makes sense after that, well, if that's 1, 1, this can't be 0, 0 because there would be another critical point out here. We note that there's another critical point halfway between them, which, well, this crossing of two contour lines seems like an interesting point. We'll talk about it in a second. In terms of the shape of the other critical points, we note that we're going downhill as we move from higher contour levels, 3, 2, 1, 0, -1. So this would be a local minimum. And likewise, this is symmetric with it. 1, 0, -1. We're going downhill again. So this would also be a local minimum. This one here is a different kind of beast. Let's emphasize that. It's certainly not a local max or min. We can see that in two ways. First off, it's not presenting itself in the classic way on a contour diagram of being the innermost point of a nested series of contours, like these 2 points are. And also, you'll notice that this contour here that it's on, well, the 2 contours it's on, all height 0. If we go this way, we go downhill. If we go this way, we're going uphill. So this point in no way, shape, or form can be a maximum because I can go up further when I take a step away from it. It can't be a minimum because I can go down further if I step away from it. So it is something new that we haven't seen before in terms of critical points. What would that look like? Well, I'll try to do a rough sketch here of the surface. The idea is we've got a valley and we have another valley later on, right? But overall, the entire surface is going up. So if we imagine walking between the critical points at -1, -1, and 1, 1, the point over here is the point 0, 0. So there's something interesting about that point. It's the point that we would go through if we wanted to cross over between the 2 valleys that are in our surface, but not go too high. If I wanted to just get across and then go into the next valley, I would try to cross at that point there. Why is that point better than any other crossing point? Well, because it's a local minimum in some sense in the other direction. If I want to go just as high as I need to, that's somehow a local minimum, but I'm also getting over the top between these 2 points, so in some sense it's a local maximum. So in some sense, I'm going to make this more precise later on, and let's talk about directions here. A local min in one direction and a local max in another. I'm just going to go back to the contour diagram to see how that would play out. Like I said here, if we went in this direction here, we'd be going uphill. So in some sense, I'd be going down, 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 just touching this contour, then going up, up, up. So there's a minimum in that direction. But if I was crossing from this valley to that valley, I'd be going up, 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 hitting height 0, and then starting down again. So there's something about some property that feels like it's a combination of 2 critical point types, a min and a max, somehow involved with this. We'll take a closer look at that in the next few pages.